So sometimes we have molecules that are enantiomers, okay? So this is a mirror image, right? So, and if you look at, the stereocenter for carbon 2 here, right? For this one, if I switch that hydrogen to the back and I make the OH go over there, it's 1, 2, 3. So, so for that one, you've got a 2R. And for this one, if you switch that H to the back, then your OH comes over there. So then it's 1, 2, 3. So it's going clockwise. So that is 3R. And so for this one, again, switch that H to the back. So the OH goes over there. So it's 1, 2, 3. So it's going counterclockwise. So this carbon 2 is an S stereocenter. And then for this one, we switch that H around to the back. So the OH comes over here. And so it'd be 1, 2, 3, so it's going counterclockwise, so then that one is a 3S. So if you have a 2R with a 3R and a 2S with a 3S, and they are mirror images of each other, then they are enantiomers. Now if you look at this other one over here, technically, these are the exact same thing, okay? Because all you would have to do, if you take that molecule and you flip it upside down, or I'm sorry, not flip it, if you turn it 180 degrees vertically, that is the same thing. And the reason is there exists a plane of symmetry within the molecule, so the top part and the bottom part are identical, okay? So since you can rotate it and you have another plane of symmetry where it's completely identical with the top and the bottom, you have symmetry. This is achiral, okay? And these are identical. Make sense? So they are the same thing. Okay, so now it's important to note, okay, so many stereoisomers, they will have different physical properties, okay? But if you have enantiomers will have the exact same. So if you have a positive and negative, so like an R and an S enantiomer, they have the same physical properties. But if you have a meso enantiomer in there that has the same formula but it's arranged slightly differently, if you have a meso, it will have different physical properties. It'll be slightly different, okay? And its specific rotation will also look like 0. It will not be optically active either, okay? It just won't be. And if you have a racemic mixture of both the positive and the negative enantiomers, it will also not be optically active because a racemic mixture will have equal amounts of the exact same levo and dextro rotary positions to make them the same optics with the same degree, but opposite directions. Okay, so again, that plane of symmetry through the middle, if you have the same thing on the top and the bottom, that's called a meso stereoisomer. Meso stereoisomer, okay? And again, you need to look at the different properties there, right? So, okay, the next little now you try, right? It says, I'm going to try and cover up my answers here. Okay, so if you look at, it says, does cis 1,2-dimethylcyclobutane have any stereocenters and is it chiral? So if you drew it out, okay, you would have, I drew this to where it's kind of three-dimensional, but I put part of it towards the back and the one towards the front I made a very dark line. So this is cis because my two methyl groups are above a plane of symmetry through the molecule, okay? So that's what makes it cis. Now, if I drew a plane of symmetry perpendicular to that through the molecule, they are identical on both sides, okay? So if I look from this portion right here, okay, if I look at this half of the molecule, so if I have my plane of symmetry going through that guy, then I've got this on this side with a methyl and this on this side with no methyl. Okay, so then I've got different stuff here, 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 and here. So that is a stereocenter. If I draw my plane of symmetry through there, Then on this side, I've got only hydrogens, and on this side, I've got a methyl. So you have different stuff here, here, the methyl, and the hydrogen. So that is also a stereocenter. So it does have two stereocenters. And it has identical sides. So it has two stereocenters, but it's symmetrical. So it's meso. Okay? So that's what that means. Two stereocenters, but it's symmetrical. You have an actual plane of symmetry where both sides of the molecule are exactly the same. So it's a meso compound, or a meso stereoisomer. Okay. And then, okay. So if you have more than two stereocenters, you will have more stereoisomers for a molecule. So here's cholesterol, and cholesterol has actually 8 different stereocenters. 8 different ones. So the way you calculate how many stereocenters you have, how many stereoisomers you have, you take the number 2 and you raise it to the power of n, okay, to find how many stereoisomers you have. So n would be the number of stereocenters. So 2 to the 8, that means there would be 256 stereoisomers for cholesterol. But only one is found in nature, and that's probably having to do with a lot of the steric hindrance that would be placed in different places if you tried to rotate this, and the fact that there are so many pieces of it that are cyclic, and there's a double bond. So it's going to be really hard to make anything else out of that. Okay, now it says now you try, and of course you see my answer, sorry. But it says you have this nandrolone molecule, and so if you find all the stereocenters, so you can pause it and try to find them all, but I found 6. So if you have 6 stereocenters, 2 to the 6th is 64, so there are 64 stereoisomers that would exist that can be found. And again, not all of those will be found in nature, because look at all the cyclic parts to this. And look at, there's a double bond, and look at that, there's a carboxyl group, carbonyl group. So, yeah. Anyway, okay. So, let's see. So, resolution of stereoisomers. Resolution, just all this means is like separation, okay? So, if you're trying to separate your stereoisomers, okay, it's hard to do this. Okay, and this is what we're talking about, that this is kind of a big moneymaker. If you have a lot of, if you have like a racemic mixture of 2 enantiomers, you want to try to separate them so you get just the plus and the minus, the optically active, so the D and the L, okay? So how do you do that? It says you can have an acid-base reaction with a racemic mixture of carboxylic acids with a chiral amine. So what is an amine? It's something with an N with some H's on it. That's really all it is, okay? Now, different amines will give you different things, okay? So if you just use, it says racemic lactic acid with achiral methylamine will lead to a racemic mixture of salts. Well, then you can precipitate out the salts, and then you can do what Pasteur did and just actually separate them according to their shape and size. But that's kind of a pain in the butt to do. I wouldn't probably do that. I mean, if it were for money, maybe. But they say it's kind of like as if you had those chiral things that are your hands, right? They're mirror images of each other. If you had in that hand and you picked up a ball, it's still going to be a mirror image. But now it's a salt, and salts are a little bit easier to isolate. Okay, so you have a quick little example here, right? So you've got the R and the S enantiomers of lactic acid. If you add methylamine, you end up with this hydrogen on each one of them goes home with NH2, and so that becomes NH3, so your N becomes positively charged and that oxygen becomes negatively charged, okay? So you'd end up with an R salt and an S salt. These are still enantiomers, guys. So enantiomers, they have similar physical properties. That's still going to be really hard to separate. So that may not be the best amine to use to separate these. So if you use something that maybe would make it a little harder to make a mirror image out of. That may be better. So if you react lactic acid with R1 phenylethylamine, which is chiral, you end up with 2 diastereoisomers. Diastereoisomers have different physical properties, so they're much easier to separate. So instead of using the methylamine like we used here, we're going to use that fellow. And when you do that, you end up with an R stereocentered salt. And this one you end up with an R stereocenter salt. These would be diastereoisomers. So they will have different melting points, different boiling points. They might even have a different reactivity, and of course they will have different, if you have them together in a mixture, they will not be optically active, but each one individually can be. So anyway, so that might be easier to separate if they have different physical properties. So that's what I would suggest, just maybe do something with a bigger salt. It's still an amine because you got the NH2, but it's even better because you've got this benzene group on it that's really hard to flip around because it's so much steric hindrance. Okay, moving on. Okay, so you have an example. Let me get my blue paper again. There we go. Okay, so you have a little example, okay? It says, suppose racemic lactic acid reacts with methanol to form an ester methyl lactate. And what stereochemistry would you expect the products to have? So here I've got my S lactic acid and my R lactic acid. And if I'm adding this to it, then I'm basically cleaving off this hydrogen, right, from each one. And I'm adding this OCH3. Okay, so I end up with CO. Keep that O. I'm sorry, we're cleaving off an OH. So we're cleaving off an OH from each of these and adding an OCH3. So we're adding this part. Well, what do you think OH and H make? Because this part cleaves off, right? You get some water, okay? So you get, technically you're going to get H2O out of this. And I think you would have to do this in an acid catalyst. That's probably what I would use. But anyway, so you end up, because this was, let's see, when we rank this, this is rank 1, this is rank 2, this is rank 3. We rank this is 1, 2, 3. When you put that OCH3 there instead of the OH, when you rank these, this is still 1, 2, 3, and this is still 1, 2, 3. So you still end up with the exact same stereochemistry. So you're still going to have a racemic mixture of S and R enantiomers when you make your methyl lactate. Cool, cool, cool? Okay. All right, and then we talk a little about chirality in nature. Oopsie, sorry, I didn't mean to show you the answer to that. Okay, so we talk about chirality in nature. So different stereoisomers that have a chiral molecule have different biological properties. So for instance, limonene in oranges, it smells kind of piney scented, and the limonene in lemons, that smells very, very lemony. Like you've smelled a lemon, you know lemons are very, very powerful. So even though these are enantiomers, they have a different odor. That is a physical property, technically, okay? Prozac. If you have heard of Prozac, Prozac is an antidepressant. It has, it actually has a bunch of different stereoisomers because it has a couple of different stereocenters in here. But the S-fluoxetine will actually prevent migraine, but most of the time you just have a mixture of S and R. So the S and R mixture together works well as an antidepressant, but if you can separate out just the S, you'll end up with a medicine that can prevent migraines. Obviously, separating out these two enantiomers would be a very big task. So Prozac is significantly cheaper than S-fluoxetine. S-fluoxetine takes a lot to resolve that enantiomeric mixture. Okay. All right, and pretty sure you probably know how enzymes work. A lot of you have had AP Bio, but Chiral molecules, especially for biomolecules, they have to fit into a chiral receptor at a target site. So it's like enzymes trying to fit into a specific place for a protein. If they don't fit, then they don't work. They don't become active. So if you have the right shapes for things, for the enzymes, they'll fit together, and that isomer can fit, and it will activate that protein to do what it does. But if you have a different isomer and you've mismatched one of these places, it will not fit, and that will not happen. Okay? And then, of course, you have your review of different types of isomers. And constitutional isomers is what we've already done in the past. That's where you have the similar or same formulas, but a completely different rearrangement of atoms, so you have completely different properties for those. And then you have stereoisomers, enantiomers, non-superimposable mirror images, and they are chiral. Diastereoisomers, they are non-superimposable, and they are not mirror images. Okay? And then you have cis-trans diastereoisomers. You can have a double bond or some kind of a ring structure. And then chiral diastereoisomers, they have multiple stereocenters, but sometimes those chiral stereoisomers, you can have another plane of symmetry where you have identical pieces on the top and the bottom, which makes a mesostereoisomer. So you need to be ready for those too.